In 1967, a graduate student named Jocelyn Bell was analyzing radio telescope data when she noticed something unusual. A signal, repeating every 1.337 seconds with clockwork precision. So regular that her first thought was interference, maybe a satellite or terrestrial radio sources. But the signal persisted, night after night, always from the same position in the sky, rising and setting with the stars. Bell and her advisor, Anthony Hewish, half-jokingly called it LGM-1, Little Green Men 1. The signal's regularity suggested intelligence, perhaps an alien beacon transmitting across the galaxy. Then they found another one, and another, and another. 4 sources scattered across different parts of the sky, each pulsing with different periods. The alien hypothesis collapsed. 4 separate civilizations all deciding to broadcast radio signals seemed absurdly unlikely. What Bell had discovered was something far stranger than aliens: dead stars. Remnants of supernova explosions crushed by gravity into objects so dense that a teaspoon would weigh 1 billion tons on Earth. Stars where the laws of physics operate at extremes we can barely comprehend, where gravity is strong enough to warp space-time into steep curves, where matter exists in states that cannot be reproduced in any laboratory. Neutron stars, and their observable manifestation, pulsars. Today, we explore objects that pack more mass than the Sun into a sphere the size of Manhattan, stars that spin hundreds of times per second, magnetic fields 1 trillion times stronger than Earth's, and physics so extreme it bridges quantum mechanics and general relativity in ways we're only beginning to understand. This is the story of the densest, strangest, most extreme objects in the universe that aren't black holes.
Stars live by converting hydrogen to helium through nuclear fusion. This process generates outward pressure that balances gravity's inward pull. When fusion stops, gravity wins. For stars like our Sun, about 1 solar mass, the collapse halts at the white dwarf stage. Electron degeneracy pressure, a quantum mechanical effect arising from the Pauli exclusion principle, prevents further compression. The result, an Earth-sized sphere of carbon and oxygen with density around 1 ton per teaspoon. For stars above 8 solar masses, the ending differs dramatically. When these massive stars exhaust their nuclear fuel, no quantum pressure can stop the collapse. The core implodes in less than a second, compressing to nuclear densities. Electrons and protons merge into neutrons through a process called neutronization. The infalling outer layers bounce off this incompressible nuclear core, generating a supernova explosion visible across millions of light years. What remains is a neutron star, 10 to 20 kilometers in diameter, containing 1.4 to 2.5 solar masses. The density exceeds that of atomic nuclei. You could fit all of humanity into a volume the size of a sugar cube. A teaspoon of neutron star material would weigh about 1 billion tons, roughly the mass of Mount Everest, compressed into something you could hold in your hand. Assuming, of course, its gravity didn't immediately pull you into an infinitely thin stream of atoms.
Neutron stars aren't uniform spheres of neutrons. They have layers, each with distinct physics. The crust, outer 1 kilometer. Despite the name, this is no ordinary crust. Densities start at around 10 to the 6th grams per cubic centimeter at the surface and increase to 10 to the 14th deeper down. The outer crust consists of a lattice of atomic nuclei, mostly iron at the surface, transitioning to increasingly neutron-rich isotopes deeper down, immersed in a sea of electrons. Below about half a kilometer, neutrons begin dripping out of nuclei. Free neutrons exist alongside nuclei in what's called the inner crust. This material is a superfluid. It flows without viscosity, exhibiting quantum behavior on macroscopic scales. The outer core. Here, densities reach 10 to the 15th grams per cubic centimeter. Matter consists primarily of neutrons, with small fractions of protons and electrons maintaining charge neutrality. Both neutrons and protons form superfluids and superconductors, respectively. These quantum condensates allow the interior to conduct electricity with zero resistance and flow without friction. The inner core. At densities above 10 to the 15th grams per cubic centimeter, we enter unknown territory. The equation of state, the relationship between pressure and density, becomes uncertain. Possible exotic states include pion condensates, kaon condensates, and hyperons, particles containing strange quarks. Deconfined quark matter, the quark-gluon plasma. Some models suggest the very center might contain absolutely stable strange quark matter. Others predict more conventional neutron superfluids. We don't know. The densities exceed anything achievable in particle accelerators. Nuclear physics enters regimes where theory provides limited guidance.
Neutron stars inherit angular momentum from their progenitor stars. As the core collapses, conservation of angular momentum spins it up dramatically, much like a figure skater pulling in their arms. The result? Rotation periods from milliseconds to seconds. Some neutron stars spin 716 times per second. That's faster than a kitchen blender. Neutron stars also inherit and amplify magnetic fields. When the stellar core collapses from perhaps 500,000 kilometers to 20 kilometers, magnetic flux is conserved. The field's strength increases by a factor of 10 to the 12 or more. Surface magnetic fields reach 10 to the 8th to 10 to the 15th Gauss. For comparison, Earth's magnetic field is about 0.5 Gauss. A refrigerator magnet is about 100 Gauss. At 10 to the 12 Gauss, typical for pulsars, the magnetic field energy density exceeds the rest mass energy density of matter. The field can rip atoms into elongated shapes. Chemistry becomes impossible. Now, combine rotation and magnetic field. The neutron star's magnetic axis typically doesn't align with its rotation axis, much like Earth's magnetic poles don't align with geographic poles. Charged particles near the surface are accelerated along magnetic field lines toward the magnetic poles. Near the poles, these particles radiate intense beams of electromagnetic radiation, primarily radio waves, but also visible light, X-rays, and gamma rays. As the star rotates, these beams sweep through space like a lighthouse. If Earth happens to lie in the beam's path, we detect regular pulses, hence pulsars. The pulse period equals the star's rotation period. The stability rivals atomic clocks. PSR B1913+16, the first binary pulsar discovered, maintains timing precision to within microseconds over decades. When Jocelyn Bell Burnell discovered the first pulsar in 1967, she was a 24-year-old graduate student at Cambridge. The discovery came from analyzing pen and ink chart recordings, miles of paper showing squiggly lines representing radio signals. Modern astronomers use computers for such analysis, but Bell examined these charts by eye.
She noticed a scruff, a slight irregularity in the baseline that appeared repeatedly at the same sidereal time. Sidereal time accounts for Earth's rotation relative to the stars rather than the Sun, indicating the source was astronomical. Further observations revealed the signal, sharp pulses separated by exactly 1.337 seconds. The regularity was unprecedented. No known astronomical object varied so precisely. Natural explanations seemed inadequate. The LGM hypothesis, half serious, half joke, briefly gained traction. Within months, Bell found 3 more pulsars. The discovery was clearly astronomical, not extraterrestrial intelligence. In 1974, Anthony Hewish received the Nobel Prize for the discovery of pulsars. Jocelyn Bell was not included, despite being the person who actually found them. This omission remains controversial. Bell herself has handled it with grace, noting that student contributions often get overlooked and that her career didn't suffer from the exclusion. Nevertheless, the physics community widely acknowledges that Bell made one of the most significant astronomical discoveries of the 20th century. Today, over 3,000 pulsars are cataloged. We've mapped their distribution across the galaxy. We've identified exotic variants, millisecond pulsars, magnetars, pulsar binaries. Each adds detail to our understanding of physics at extremes. Determining neutron star masses was initially difficult. A single isolated pulsar reveals its rotation period, magnetic field strength, and distance, but not directly its mass. Binary systems provided the breakthrough. PSR B1913 plus 16, discovered in 1974 by Russell Hulse and Joseph Taylor, consists of 2 neutron stars orbiting each other with a period of 7.75 hours. By measuring Doppler shifts in the pulsar's signal as it orbits, astronomers determined both stars have masses around 1.4 solar masses. This measurement constrained the equation of state. If neutron stars were much less massive, the required central densities would be too low. If much more massive, they'd approach the theoretical maximum before collapsing into black holes. Later observations refined this picture. PSR J0348 plus 0432, a pulsar in a binary with a white dwarf, has a precisely measured mass of 2.01 plus or minus 0.04 solar masses. PSR J0740 plus 6620 tops the list at 2.14 plus or minus 0.10 solar masses. These measurements push against theoretical limits. Above roughly 2.5 solar masses, no known equation of state can prevent collapse to a black hole. The maximum mass depends on interior composition, specifically how matter behaves at densities exceeding atomic nuclei. Pulsars occasionally glitch, sudden increases in rotation rate occurring on timescales of seconds. The Vela pulsar, one of the brightest pulsars in the sky, glitches approximately once every 3 years. Its rotation period decreases by a few microseconds during each glitch, then gradually recovers over weeks to months. Glitches reveal internal structure. The leading explanation involves the superfluid interior. As the pulsar radiates energy and slows down, the superfluid interior, which cannot easily lose angular momentum, continues rotating at nearly its original rate. Eventually, the velocity difference between crust and interior grows too large. The superfluid couples suddenly to the crust through quantum vortex unpinning, transferring angular momentum and spinning up the observable crust. This model predicts glitch magnitudes, recovery timescales, and frequencies matching observations. Glitches provide our only direct probe of neutron star interiors. External observations can't penetrate the crust, but glitches reveal the superfluid core's behavior. Some pulsars spin extraordinarily fast. PSR J17482446 AD holds the record, 716 rotations per second. At this rate, the star's equator moves at roughly 20% the speed of light. Surface gravity barely holds the star together against centrifugal forces. These millisecond pulsars pose a puzzle. Most neutron stars spin down over time as they radiate energy. How do some spin up to millisecond periods? The answer? Accretion from a companion star. Millisecond pulsars typically reside in binary systems with white dwarf companions. Early in the binary's history, the companion was a main sequence star. As it evolved, it expanded, transferring matter onto the neutron star. Infalling matter carries angular momentum, spinning up the neutron star like water hitting a turbine. Over millions of years, this process accelerates the neutron star to millisecond periods. Eventually, the companion exhausts its outer layers, leaving a white dwarf. The neutron star, now spinning rapidly, continues as a millisecond pulsar. This process is observable in real time. X-ray binaries show neutron stars accreting matter and spinning up. They're millisecond pulsars in formation. In the 1990s, astronomers discovered a new class of objects, soft gamma repeaters, SGRs, and anomalous X-ray pulsars, AXPs. These objects emit X-rays and gamma rays far more intense than their rotation could power. Their energy source remained mysterious until observations revealed their magnetic fields. Surface magnetic fields exceed 10 to the 14 Gauss, hundreds of times stronger than typical pulsars. These are magnetars, neutron stars where magnetic energy dominates. In December 2004, SGR 180620 erupted. In 0.2 seconds, it released more energy than the sun emits in 100,000 years. The burst saturated every X-ray and gamma-ray detector in the solar system. Instruments on spacecraft were temporarily blinded. The burst was visible from 50,000 light-years away, halfway across the galaxy. Magnetar flares involve magnetic field reconfiguration. Stresses build as the ultra-strong field evolves and the star's crust cracks. Sudden magnetic reconnection releases stored energy in seconds. The magnetic field itself is so strong that it affects space-time. At 10 to the 15 Gauss, the field energy contributes measurably to the star's gravitational field. Quantum electrodynamics predicts vacuum polarization at these field strengths. Virtual electron-positron pairs alter electromagnetic wave propagation. Light doesn't travel through the magnetar's magnetosphere the same way it does through normal space. PSR B1913 plus 16, the Hulse-Taylor binary pulsar, provided the first indirect detection of gravitational waves. As the two neutron stars orbit, they emit gravitational radiation, ripples in spacetime, predicted by general relativity. This emission carries away energy, causing the orbit to decay. Over decades of observations, the orbital period decreased exactly as general relativity predicts. The two stars are spiraling together at 3.1 millimeters per orbit. In about 300 million years, they'll merge. This measurement earned Hulse and Taylor the 1993 Nobel Prize. It confirmed gravitational waves exist, even though they hadn't been directly detected yet. In 2015, LIGO, Laser Interferometer Gravitational Wave Observatory, directly detected gravitational waves from two merging black holes. In 2017, LIGO and Virgo detected GW170817, gravitational waves from merging neutron stars. Optical telescopes observed the Kilonova, the electromagnetic counterpart, providing the first multi-messenger observation of a neutron star merger. This event confirmed that neutron star mergers produce heavy elements like gold and platinum through rapid neutron capture nucleosynthesis. The equation of state describes how matter behaves at extreme densities. It's the relationship between pressure, density, and temperature. For normal matter, equations of state are well understood. Water's equation of state is tabulated in engineering handbooks. For neutron star cores, we're guessing. Quantum chromodynamics, CQD, the theory of strong nuclear forces, governs neutron star interiors, but CQD calculations at neutron star densities remain computationally intractable. Observations constrain possibilities. Mass measurements set minimum stiffness. If the equation of state were too soft, neutron stars couldn't support 2+ solar masses without collapsing. Radii measurements from X-ray observations of neutron star surfaces provide additional constraints. NICER, NICER, on the International Space Station measures radii to within kilometers. Tidal deformability from gravitational wave observations during mergers reveals how easily gravity distorts neutron stars. Stiffer equations of state resist deformation. Softer ones deform more. Combining these constraints narrows allowed equations of state. Current data suggest radii of 11 to 13 kilometers for 1.4 solar mass neutron stars. This allows us to rule out some exotic interior models while keeping others viable. Pulsars don't exist in isolation. They're surrounded by pulsar wind nebulae, vast clouds of relativistic particles accelerated by the pulsar's electromagnetic fields. The Crab Nebula, remnant of a supernova observed in 1054 CE, contains the Crab pulsar, spinning 30 times per second. The pulsar powers the nebula's glow, pumping 10 to the 38th ergs per second into the surrounding material. Without the pulsar's energy input, the nebula would fade in about 50 years. We know this because we can calculate the nebula's energy content and cooling rate. The pulsar replenishes this energy continuously, maintaining the nebula's luminosity over centuries. Pulsar wind nebulae provide laboratories for studying particle acceleration. Electrons and positrons accelerate to 99.9999% the speed of light. These particles spiral around magnetic field lines, emitting synchrotron radiation visible from radio through gamma rays. The details of particle acceleration remain unclear. The pulsar somehow accelerates particles to PeV, 10 to the 15 eV, energies, millions of times more energetic than the Large Hadron Collider, collisions. Some millisecond pulsars are destroying their companions. Black widow pulsars emit intense pulsar winds that ablate their companion stars, typically low-mass white dwarfs or main sequence stars. The companion evaporates over millions of years. PSR J1959 plus 2048, a black widow pulsar, has reduced its companion to just 0.02 solar masses, 20 times Jupiter's mass. In another few million years, the companion will vanish entirely. Redback pulsars represent a similar phenomenon with more massive companions. The pulsar alternately accretes matter from the companion and blasts it away with pulsar winds. These systems are laboratories for studying matter under extreme irradiation. The companion star's surface temperature varies by thousands of degrees, depending on whether it faces the pulsar. Some companions show heavy element abundances enhanced by pulsar wind interactions. The pulsar effectively strips and reprocesses the companion's outer layers. These systems also provide mass measurements. By observing eclipses and Doppler shifts, astronomers determine precise orbital parameters and stellar masses. The structure of neutron stars is governed by the Tolman-Oppenheimer-Volkoff equations, derived from general relativity. These equations balance gravity against internal pressure. Unlike simple hydrostatic equilibrium for normal stars, the TOV equations account for relativistic effects. Pressure contributes to gravity, and space-time curvature affects pressure gradients. Given an equation of state, the TOV equations determine the mass-radius relationship. Input a central density, and the equations calculate the resulting mass and radius. The equations predict a maximum mass. Above this limit, no internal pressure can prevent collapse to a black hole. For realistic equations of state, this maximum lies between 2 and 3 solar masses. Observations of 2+ solar mass neutron stars rule out soft equations of state. We know neutron star matter is stiffer than some models predicted. But we don't know how much stiffer. Observations haven't yet found a neutron star massive enough to test the absolute maximum. Inside neutron stars, matter exists at densities where individual nucleons overlap. At normal nuclear densities, 10 to the 14 grams per centimeter cubed, nucleons remain distinct. Inside neutron star cores, greater than 10 to the 15 grams per centimeter cubed, this distinction blurs. Nucleons aren't fundamental. They're composed of quarks bound by the strong force. At extreme densities, quark-quark separations approach the scale where confinement breaks down. In normal matter, quarks are permanently confined inside protons and neutrons. You can't isolate a single quark. The strong force grows stronger with distance, making separation impossible. But at neutron star core densities, quarks might deconfine. The distinction between individual nucleons vanishes, creating a quark-gluon plasma. Alternatively, strange quarks, heavier cousins of the up and down quarks in normal matter, might appear. Adding strange quarks creates hyperons, or strange quark matter. Absolutely stable strange quark matter, if it exists, could be more energetically favorable than normal nuclear matter. In this scenario, neutron stars would actually be strange stars, bound by the strong force rather than gravity, with densities approaching nuclear matter everywhere. We don't know which scenario is correct. observations can't yet distinguish between different core compositions.
Neutron star magnetic fields are the strongest in the universe outside black hole event horizons. The origin of these fields remains debated. Possibilities include flux conservation. If the progenitor star had a magnetic field of 10 Gauss, typical for massive stars, collapsing from 500,000 kilometers to 10 kilometers amplifies the field by 10 to the 12th, yielding 10 to the 13 Gauss. Dynamo mechanisms, convection in the proto-neutron star immediately after formation, could generate magnetic fields through dynamo action. Fallback accretion, material falling back after the initial supernova, might carry angular momentum, generating magnetic fields through accretion disk processes. Magnetar fields, 10 to the 14 to 10 to the 15 Gauss, likely require additional amplification mechanisms, possibly related to rapid rotation or unusual supernova dynamics. Once established, magnetic fields decay over time. Ohmic dissipation, resistance in the crust, causes field decay on million-year timescales. Hall drift, a quantum mechanical effect in strong magnetic fields, reorganizes field geometry without changing total magnetic energy. This creates complex surface field structures and may trigger magnetar flares. Young pulsars have stronger fields. Old pulsars have weaker fields. The relationship between age and field strength matches decay models.
When two neutron stars spiral together and merge, they create conditions unmatched anywhere else in the universe. As the stars approach, tidal forces deform them. Material is ejected, about 1 to 10% of a solar mass, expanding at 10 to 30% the speed of light. This ejected material contains free neutrons, lots of them. Densities far exceed anything in normal stellar environments. Neutrons bombard seed nuclei, iron group elements from the neutron star crusts. Neutron capture occurs faster than radioactive decay. Elements climb the periodic table rapidly. This process, rapid neutron capture nucleosynthesis, or R process, creates elements heavier than iron: gold, platinum, uranium, thorium. Half the elements in the periodic table above iron originate in neutron star mergers. The R process also produces radioactive isotopes that decay over hours to weeks, releasing energy and making the expanding ejecta glow. This is a kilonova, visible across hundreds of millions of light years. GW170817, the 2017 neutron star merger observed by LIGO and optical telescopes, produced approximately 10 Earth masses of gold and 100 Earth masses of platinum. Your gold jewelry was forged in a neutron star merger billions of years ago, long before Earth formed. Neutron stars provide extreme gravity laboratories for testing Einstein's theory. General relativity has passed every test in the solar system and beyond, but these are weak field tests. Gravitational fields in the solar system are gentle. Space-time is nearly flat. Near neutron stars, space-time is severely curved. Gravitational redshift exceeds 20%. Light from the surface loses 1/5 of its energy climbing out of the gravity well. Orbital dynamics in binary pulsars reveal relativistic effects. Periastron advance, the orbit's ellipse rotates by 4.2 degrees per year for PSR B1913 plus 16, observable over a few years, versus Mercury's 43 arcseconds per century, requiring decades to detect. gravitational redshift and time dilation. Pulses from the moving pulsar experience varying gravitational fields and velocities, producing periodic shifts matching relativistic predictions. Orbital decay from gravitational wave emission. The orbit shrinks at exactly the rate general relativity predicts. So far, general relativity passes all tests. Deviations remain below 0.1% in most measurements. Alternative gravity theories, scalar tensor theories, F of R gravity, others, predict small differences from general relativity at strong fields. None are observed. Neutron stars are proving Einstein right in conditions he could never have imagined testing. Rotating neutron stars with asymmetries, bumps on their surfaces, or internal irregularities should emit continuous gravitational waves. Unlike brief chirps from mergers, continuous waves have constant frequency and amplitude, lasting for years or longer. LIGO and Virgo have searched for such signals. None detected yet. This non-detection is informative. It constrains surface asymmetries to less than 1 millimeter for nearby millisecond pulsars. 1 millimeter might sound tiny, but on a 20-kilometer sphere, it's remarkably smooth. Earth's surface, scaled to the same relative size, has kilometer-high mountains. Neutron star crusts are rigid, stronger than steel by factors of 10 to the 10. They can support larger asymmetries than detected limits allow. The lack of detection suggests either 1. Crustal mountains are smaller than nuclear physics predicts. 2. Gravitational wave emission efficiently removes any asymmetries. Or 3. Our detection sensitivity isn't yet sufficient. Future gravitational wave detectors, Einstein telescope, Cosmic Explorer, will push sensitivity deeper. If continuous waves exist at predicted levels, they'll find them. Detecting continuous gravitational waves would reveal interior physics. The size of sustainable asymmetries depends on crust strength, superfluid dynamics, and magnetic field interactions with matter. It's another probe of conditions we can't replicate in laboratories.
Neutron stars have a mass limit. Exceed it, and collapse to a black hole is inevitable. But what happens at that boundary? One possibility, a direct transition. Add mass to a 2.5 solar mass neutron star, and it collapses instantly to a black hole. Another, a phase transition. At maximum mass, matter in the core transitions to a more exotic state, quark matter, or absolutely stable strange matter. This transition might create a briefly stable object before ultimate collapse. A third, a stable hybrid star. If quark matter transitions are first-order phase transitions, like water freezing, the core might convert to quark matter while maintaining stability. The result would be a hybrid star, neutron matter in the outer core, quark matter in the center. Some equations of state predict twin stars, two stable solutions at the same mass, one ordinary neutron star and one hybrid star. Observationally distinguishing them would be difficult, but possible through radius measurements or cooling rates. Finding a neutron star above 2.5 solar masses would revolutionize nuclear physics. It would demonstrate that matter at extreme densities is stiffer than current theory predicts. Conversely, finding none might mean the maximum mass is lower than theoretical predictions, around 2.2 solar masses. Either way, observations constrain theory.
This sounds absurd. Obviously, neutron stars have crusts. We've discussed them extensively. But consider, the crust exists because there's a pressure gradient. Deeper layers support weight from above. At maximum mass, Space-time is so strongly curved that pressure gradients become extreme. Some models suggest the crust might not exist for the most massive neutron stars. Matter transitions directly from vacuum to nuclear density at the surface. If true, such stars would have extraordinary properties. The surface would be pure neutron matter, not a solid lattice. Temperature variations would propagate instantly through the superfluid interior. We don't know if such objects are possible. The physics at maximum mass remains speculative. But it's a question observations might answer. X-ray observations of massive neutron stars could reveal whether their surfaces behave like crusted objects or something stranger.
Inside neutron star cores, the speed of sound, the velocity at which pressure waves propagate, approaches the speed of light. General relativity doesn't forbid sound speeds approaching light speed, but causality imposes limits. Information cannot propagate faster than light. In some equations of state, particularly those with phase transitions, sound speeds exceed the speed of light. This violates causality. These equations of state must be wrong. Physical law doesn't permit superluminal information transfer. But ruling out such equations requires understanding the connection between microscopic nuclear interactions and macroscopic sound speeds, a problem at the frontier of theoretical physics. Recent observations have tightened constraints. The allowed range of equations of state narrows with each new measurement. Within a decade, observations may definitively determine whether exotic quark matter exists in neutron star cores, or whether they're composed entirely of neutrons with small admixtures of protons. This would answer questions about quantum chromodynamics that no Earth-based accelerator can address.
Neutron stars are laboratories for physics at extremes. They contain matter at nuclear densities, magnetic fields that warp spacetime, rotation rates approaching relativistic velocities, and gravitational fields strong enough to bend light by measurable angles. Pulsars, their observable manifestation, provide precision clocks, gravitational wave sources, and probes of interstellar space. They've tested general relativity to unprecedented accuracy. They've shown us how heavy elements form. They've revealed quantum superfluids on stellar scales. Yet, fundamental questions remain. We don't know the exact composition of neutron star cores. We don't know the origin of magnetar fields. We don't know why some pulsars glitch and others don't. Future observations will address these questions. NICER continues measuring neutron star radii from the International Space Station. Next-generation gravitational wave detectors will observe neutron star mergers with unprecedented detail. Radio telescope arrays will discover thousands more pulsars, mapping the galaxy's neutron star population. X-ray and gamma-ray observatories will monitor magnetars, catching flares and mapping magnetic field evolution. Each observation constrains theory. Each measurement narrows the range of possibilities. Neutron stars bridge quantum mechanics and general relativity. They're quantum objects, exhibiting superfluidity, superconductivity, quantum vortices. Yet, they're governed by space-time curvature. They're microscopic physics writ large. Understanding them fully requires a theory of quantum gravity, something we don't yet have. But we're getting closer. Neutron star observations provide boundary conditions for that ultimate theory. They're not just dead remnants of stars. They're active, dynamic laboratories where the universe experiments with physics at extremes we can barely imagine, much less reproduce. And we're privileged to observe them, study them, and learn from them.